vamos a proceder con la moderadora, la doctora Jessica López, se encuentra por ahí, y la ponente, la doctora Eden. Doctora Eden, ya la vemos.
Hola, gracias.
Hola. ¿Quiere, doctora, empezar a compartir pantalla para hacer pruebas? Adelante.
Yes. Can you see my screen?
Yes.
Okay, thank you. Jessica says that she doesn't have access to speak. You can do it here if you want.
Por favor, si pueden subir al moderador. Ya estaba como Jessica López Espejel.
I think she needs permission to be able to unmute herself.
One moment, please.
Ya está arriba.
Doctora Jessica López Espejel, ya está usted como panelista, moderador.
Okay. Sí, gracias.
Ya te escuchamos. Entonces, cuando tú gustes.
Bueno, buenas tardes. Comenzamos con la ponencia de Irene Belouadah, quien es doctora en inteligencia artificial por el MIT de Atlantique, Francia, y bueno, se graduó en 2021. También Irene Belouadah tiene 2 maestrías. La primera es en aprendizaje automático por Francia y la segunda es en inteligencia artificial por Argelia. Ella actualmente es investigadora en Datakalab en París, Francia, y su investigación se centra en el aprendizaje continuo aplicado a la clasificación de imágenes y a la detección de objetos. Su principal interés está en utilizar el aprendizaje profundo para abordar problemas del mundo real, especialmente los relacionados con la visión por ordenador. Thank you, Edie, for staying here with us. And well, I think we can start with your presentation.
Thank you, Jessica, for the presentation. Let me just put it. Thank you. I am Eden Belouadah. Hello, everyone. Thank you for being here and for inviting me to give this talk. It's a pleasure for me to be here with you today. Today I will be speaking about continual learning. The goal of this presentation is not to dive deep in continual learning, but is to just give a clear explanation about what is continual learning, why it is important in artificial intelligence, and what are the main categories of methods that are deployed to solve this task. So don't hesitate. If you have questions, you can ask them in the chat or just in the end of the presentation. Many technological fields are evolving very quickly that push human to keep pace with them, and this development brings with it a huge increase in data. When we speak about big data or huge amount of data, it is becoming so normal nowadays. For example, in social media, billions of content is uploaded every day on platforms such as Facebook, Instagram, and so on. So this increase in data pushed humans to find solutions that are automatic in order to solve problems very quickly. And it's here where artificial intelligence became unavoidable in our world, because it helped to solve many tasks that are complex and needs lots of time for humans to do. One of the main core components of artificial intelligence is deep neural networks, or simply deep learning. It's type of neural networks that are now the most popular techniques in artificial intelligence to solve most complex tasks, and they achieved in some cases better performance than the human performance. So some applications of artificial intelligence are the classification. It's so popular task. Here in this example, we can find text classification. For example, we have just a bunch of articles from the media, and the goal of this artificial intelligence system is to sort these articles into technological, sports, or medical articles, and like this, the journalists can tackle these articles differently without to sort them manually, which takes lots of time from them. There is also voice recognition systems like Siri, Alexa, and Google Assistants, where we give an order or an instruction to this artificial intelligence by voice, and it receives this voice, and it processes it and does what it understood from our instruction. Also, one very popular recommender systems that is deployed in many of online shops like Amazon, or also in media content websites such as YouTube, are the recommender systems that help to process the human preferences and study it. For example, when we see one article in Amazon, the artificial intelligence behind these websites will check similar articles to this article that we just saw, or we showed interest in it, and it will recommend us some articles that are similar to it, in order to improve the human experience in online shops. So before to dig in details, I will say that in this presentation, I will focus on image classification with convolutional neural networks. So why image classification? It's because it's an easy task of computer vision, and it will help me to explain continual learning very easily, contrarily to other more complex tasks, such as object detection, for example. And why ConvNets? ConvNets are the most successful nowadays type of neural networks to process images, even though transformer neural networks are deployed now also for computer vision. They are still more useful in textual tasks rather than the image. So that's why the ConvNets I am invoking here. So I will not explain in detail how ConvNets work, because the goal of the presentation, as I said, is just to explain what is continual learning. Just to give a fast recap, ConvNets is composed of many convolutional layers, followed by pooling layers, and finally, in the end of the neural network, one or many fully connected layers that we call also classification layers or output layers. In this example, we have an image of a cat, and the goal of this ConvNet is to classify this image to say if it's a cat, if it's a dog, or if it's a tiger, or whatever type of animals that we are trying to recognize. So to simplify the explanation, I will just use these small graphics in blue and red to illustrate a ConvNet, even though it is not really a ConvNet, but it will help me to simplify the illustration. So as an input, we have the cat, and here as an output, we have the probabilities of predictions of this image. Here, for example, it's the neural network is saying that this image is 70% a cat and 1%, 10%, sorry, a dog, and so on. So what is exactly continual learning? Before to pass to continual learning, I need to remind very fast what is a classical training and how we pass from classical training to the notion of continuity. So here I have the same neural network that I invoked before. So as an input, we have a set of images for one or multiple classes. For example, here I have C1 that is class of cats and C2 it's a class of dog. So this constitutes my training set that I will use to train my neural network. So to do the training, we will just pass these training sets by the neural network. This is what we call the forward propagation. In forward propagation, we will compute the outputs of the neurons of the neural network, and it will give us the output predictions. Just a quick notation here. When I say neurons, I also mean the weights of the neural network or parameters of the neural network. So I will use these two terms in the next slides, parameters or weights of the neural network. So once we have the output probabilities, we compute what we call a loss function. It means how much our neural network did a mistake when it was trying to classify these images. We use this loss to compute gradients and perform what we call backward propagation. So the backward propagation helps in updating the parameters, or I would say the weights of the neural network, in order to rectify them to do a better classification in the next epoch. So epoch is just forward propagation followed by the backward propagation. So we repeat this process multiple epochs, multiple times, until the neural networks achieve to learn to distinguish between cats and dogs, and it has a very low loss rate at the end. So this is what we call the training stage. Now, for the evaluation of the neural network, we have a set of images that we call testing set. And this testing set, it contains images that can belong to either cat or dog, because we train the neural network to distinguish between these two classes. We pass our testing sets by the neural network, and the neural network provides us with the output probabilities. In this example, it's telling us that it's 90% sure that this photo belongs to a cat. And this is when we get these output probabilities, we take the class that gives the maximum output probability, and we just simply count how many images they were correctly classified in our testing set. And we would say, for example, if we have 100 images, testing images, and 75 were correctly predicted, we will say that the accuracy of our neural networks is 75%. So this is a classical evaluation in classical training of the neural network. So now, okay, we have one model that can recognize cats and dogs. It has a good level of accuracy. Now, what happens if new classes appear? What happens if now I have images of birds, of horses, of flowers, and I want to include them in my neural network? So what can I do with my model and with this data? So here is where we use or where we need continual learning. So continual learning is the ability of a neural network to learn an unlimited set of tasks that occur in stream. What does it mean? It means that we have data that doesn't stop to arrive. This is the case, for example, in the social media. The data never stop to be uploaded in the social media. And continual learning is the fact that our neural network continuously is trained on this data that occurs in stream, without having a limit of the number of data that we learn. So some applications of continual learning is robotics. Robotics, for example, we can have one robot that it's exploring the environment. So these robots can function in many environments, for example, in the house, in the garden. So this changement in the distribution of the images that he sees force him to deploy a continual learning algorithm in order to be able to continuously adapt to the changing environment. Also, we can find autonomous cars. As we know, the autonomous cars are still in development, and they are trying to develop cars that they can drive by themselves. So when we are training a car to drive autonomously, this car is trained in the beginning as an example in this image. For example, it's trained to recognize persons. It's able to recognize cars as an obstacle, but we know as the car advances in the way, we can have other types of obstacles, such as animals that cross the path, or whatever another object. So we need this continuity in training in order to train this car to autonomously drive. We also can find face recognition systems. Imagine we have in defense company, and when we have defense company, usually they use face recognition doors. Cameras that are next to the door to be able to grant the access to the people or not. So, today we have 1,000 employees, and we have an artificial intelligence that's learned how to distinguish between this 1,000 employees to grant access to them. So what happens tomorrow when this company recruits more people? In this case, we need to update our model to be able to recognize the new employees in the company. Also in the health care system, as we know, the patients continuously go to the hospital, and we need artificial intelligence systems that continuously learn the patient's data without necessarily having access to the previous data for privacy issues. So more concretely, what is continual learning? Here I have the same example that I showed before. At time step 1, we have our input data that it has 2 classes, C1 and C2, cats and dogs. So we train our neural networks like we did in classical training, and these neural networks predicts output for these 2 classes. Now, in continual learning, there isn't only one time step, but there is 2, 3, 4, 5 unlimited time steps. So in time step number 2, we have other sets of classes that appear. Here I have bird and horses that we have their own training set. So what we will do is that we will take our neural network, we will update it. It means we will just take the data of new classes, and we will update our neural network. We will train it or fine tune it, as we say, on this data. And like we can see here, now it outputs 4 probability output probabilities, each for each class that it saw. So P1, P2 are for the cats and dogs, and P3 and P4 are for the bird and the horse. And so on. Now in time step 3, we have another set of classes, not necessarily two. I'm just using it here as an illustration. We can have multiple classes or just one class at a time. And we update again our model, and now our model can predict the 6 output probabilities for the 6 classes. So as we see here, each time we add one neuron to the output layer in order to be able to classify a new class. So this is the training stage, I would say intuitive training stage, when we want to update our model continuously. Now, the different thing about the evaluation when we are doing continual learning is that, at time step 1, we have test images of cats and dogs. We pass them to neural networks, and we have our prediction. All is okay, because until now we are just doing, I will say, classical training at time step 1. The difficulties start from the time step 2, because here in the test sets, we can not only have images of horse and bird, but we also can have images of cat and dog, because this is intuitive, as we see that our model already in the past saw cats and dogs. So intuitively, we will say that now it can classify cat, dog, bird, and horse, and not only the bird and horse that it saw right now in the training stage. So in the same way, when we pass to the time step 3, we are able to give wherever image belonging to cat, dog, bird, horse, a flower, or butterfly to our model, as it already saw the other classes in the past. So this is what the logic says. But unfortunately, in the practice, is not as easy as it looks like. So the main challenge of continual learning algorithms is what we call catastrophic forgetting. And this term, it means the tendency of our neural network to underfit or simply forget past data when trying to learn a new one. What does it mean this? It means that when we fine-tune or when we train our model with the new data, it completely forgets what it learned before. That's why we use the term catastrophic. So it's not an exaggerated term. It seriously means that the neural network cannot recognize anymore what it was learned in the past. And this, as I said, it happens when we update the neural network only with the data of the new classes when it appears. So how can we measure the catastrophic forgetting, or how we can know that there is catastrophic forgetting in our neural network? This is easily observable in the output layer, in the classification layer. For example, here what I will do is that we will plot in the x-axis, well, we have the classes in the x-axis, and in the y-axis, we have the mean output probabilities of all the training set. It means here that I take all the images that I have from cats and dogs during the training state, I pass them by my neural network, and I compute the mean of probabilities P1 and P2 and check how much they are. So in the first state, as I said, it's an easy task because there is no continual learning in the first state. We have output probabilities that are comparable between cats and dogs, and this means that during the test stage, when we pass our test image by the neural network, cats and dogs, they both have, these two classes, they both have equal, I will say, equal chances to be selected during the inference. So there is no problem about it. Now, when we pass to the second incremental state in time step 2, and we compute the same mean output prediction for the classes P3 and P4 that are in blue. It means they are new classes. And we compute those of the past classes, P1 and P2. We see that there is a high imbalance in the prediction scores between the two sets of classes. And why this happens is because if we use just the data of C3 and C4 to update our neural network to train it, so also the output neurons for P3 and P4 will be updated in the time that P1 and P2 will degrade, because the neural network has tendency to too much be updated to be able to classify the new classes, and it's not able anymore to recognize the past classes. So this imbalance in the prediction scores, in the mean prediction scores while we train, this implies that when we have a test image in the testing stage and we pass it by the neural network, it will be high probably predicted as belonging to C3 and C4, even if it's not the case. It means if I have an image of a dog and I pass it to my neural network in this state, in the state number 2, it will be high probably predicted as bird or as horse, because the mean prediction scores for cat and dog are so low. Now it's the same in the task number 3. So we observe that the probability scores of past classes are so low compared to the new classes. And again, cats, dogs, birds, and horses, in this case, all of them are predicted as belonging to the class of a flower and butterfly, and this is so problematic. So one can tell me, so it's not just easier to retrain the model each time we have new classes with all the data that we saw before. It means that here in the second state, why just we don't train with cats, dogs, birds, and horses? Why we just take all this data and train our neural network with it? Well, sorry to tell you that we can't. Because in this example, it's easy to do it because we don't have too much data. But if we imagine, as I said, millions or billions of data that is uploaded in the social media every day, we can't, at each data uploaded, we retrain all the neural network on all the data of the user that it is. I will assume that it's registered, for example, in Facebook since 10 years. We can't each time retrain our neural network with this data because first, it will take lots of memory to store, and second, it will need too much computational resources in order to retrain from scratch each time. So theoretically we can, but practically it's almost impossible with big data actually. So this is the main challenge of continual learning algorithms. Here we identified some properties of continual learning algorithms that make them, I would say, more specific or hard algorithms compared to simple learning algorithms. The first one is the complexity of the neural network. When I say complexity, I mean the number of neurons or the number of parameters of the neural network. So a continual learning algorithm should have limited complexity. It means when there are new classes that appear, we are only allowed to add some the neurons in the classification layer for these classes, but we are not supposed to increase the architecture of the neural network in order to learn this new data. The second property is the memory. A continual learning algorithm should be able to work without a memory at all for the past classes, or it can work but with a fixed size memory that doesn't exceed, for example, 20 images maximum per past class. The third one is accuracy. So continual learning algorithm should be able to be performant not only on new classes but also on past classes that it saw since a long time ago. The fourth property is timeliness. It means that the neural network should be fast to include the data that is new because it can't take lots of time to include the data. Since the data continuously arrives, it should be prompt inclusion of this data in the neural network. The fifth property is the plasticity stability compromise. Plasticity, it means the ability of the neural network to adapt fast to the data to the new data that has probably a different distribution. And the stability is the fact to freeze the neural network in order to keep as much data from the past. So this is a big and difficult compromise to do. Will I change to the new data to be able to learn it, or will I stay stable in order to don't forget what I learned before? The scalability, it's the ability to learn an unlimited number of classes, or I would say at least a large number of classes. I would say at least 1,000 class or more. The main methods of the state of the art now, they are, I can categorize them in three big categories. The first one is called fine-tuning based methods. This method, they update all the neural network when the new data arrived. Here we have three subcategories. The first one, rehearsal based. It means methods that they keep a little memory for the past classes, and they use this memory to refresh the neural network. Rehearsal-free methods are the methods that do not at all use memory for the past, and they just include the data as it arrives. I mean, it's the new data to the neural network, but of course they have other techniques to tackle catastrophic forgetting. Pseudo-rehearsal-based methods are the methods that use generative models such as GANs and autoencoders in order to generate data from the past classes instead to store it in images, in memory, sorry. The second category are fixed representation based. So the representation of a neural network is all the weights that it learns until the last fully connected layer. So this is what we call the representation of the model. So as we know, the convnets, the more we train them on rich and large data, the more they have good representation, as we call it, and they provide compact presentation of the images that is of good quality. So when we speak about fixed representation, it means that the methods that they freeze the neural network up to the final layer, and they use this frozen neural network in the subsequent states in order to don't forget what was learned before. The third category are the parameter isolation-based methods, and as the name suggests, they isolate some parameters or weights of the neural networks to some classes. For example, they take some weights for the classes of the first state and some other weights for the classes of the second state. Here there are fixed networks and dynamic networks. So the fixed networks are the networks that they don't increase the architecture of the neural network, but they just share the weights between the different classes in order to don't have this interference between the weights of different classes. However, dynamic networks, they expand the neural network as the new data arrive. So I will explain a little bit in more detail all these methods in the next slides. Here I will just give simplistic illustration of the neural network. Of course, here it's not convnet. This is multi-layer perceptron, but I will just use it to simplify the explanation of the methods. So this is normally a fully connected layer, and it's not a convolutional neural network, but I will use this illustration to simplify the explanation. So the first methods are the fixed representation-based methods. So as I said, the fixed representation, the representation of the neural network are all the layers, all the hidden layers that are before the output one. So this is what we call the representation of the model. So these methods, what they do is that they train the neural network the first time on the first set of classes, in our example C1 and C2, and then they freeze the neural network. It means they won't update it anymore. It will be frozen, this part, and they will just update the part that is in purple here for the new classes that appear. So C4, C3 and C4, they will be updated. I mean, they will be learned by updating these weights, the same for C5 and C6 and so on. So as I said, the goal of these methods is like they depart from the concept of let's train our neural network on the first classes, let's freeze this neural network to don't forget the past data, and let's just update the last layers to the new data. Why exactly the last layers? Because in convnets, the first layers they include they learn, I would say, general patterns, for example, colors, edges. So they are common between different tasks, and the last layers are the ones that are specialized in the task that we want to learn. So that's why they train the final layers. The advantage of these methods, they have a complexity of the model that increases slowly. It means that they only add one neuron at each time there is a new class to be able to classify it. These methods are not dependent on a memory of the past. It means that you can have memory or you can't have a memory. They still have good accuracy, so which is good. They don't really need to keep any data from the past to have good results. and they include the new classes very fast. Why? As I said, since they freeze almost all the neural network, so there is no the back propagation will affect only few parameters, which means few computation, and we gain lots of time by using these methods. However, the big disadvantage of these methods is their scalability that depends too much on the quality of the fixed representation. It means that if this model was initially trained on big and large set of classes that is diversified, it will have a good representation in the future. But if it's trained on really few classes or very poor number of images, the representation of the model, its quality, it's not good. So if we freeze it and we just train the last layers, it will not really solve any problem of catastrophic forgetting. It will be just problem of underfitting the data. Here I just give you examples of two papers that you can read of this type of methods. The second type is fine-tuning based methods. It's the methods that they update all the neural network when the new data arrives. So the first type is rehearsal-based methods. It means that the methods that they keep a small memory of the past. As I said, it's really limited memory. In the community of incremental learning or continual learning, they use 20 images per class as a maximum. Compared to, for example, 1,000 image for bird and 1,000 image for horse, which is incomparable. So this short memory, it looks like it helps too much in tackling in tackling catastrophic forgetting, and it helps each time to refresh the memory of the neural network to don't let it forget the past classes. So the main goal is not only to train it on the new data, but also to remind the neural network what it already saw in the past. And these methods, they update all the parameters of the neural network using the data of past and new classes, plus other techniques as the distillation loss. I mean, there are many loss functions that are also used to tackle catastrophic forgetting. It's not just about to use the memory or not. The second type is rehearsal-free methods. So it's the same type of methods, it's just that they don't use at all memory for the past, which is good. But these type of methods, since they don't have any way to refresh the representation of the neural network, they just rely on loss functions to force the neural network to predict the same output probabilities for the past classes in this state. The last type of methods in this category is the pseudo-rehearsal methods. And these methods, they use, as I said, a generative model, such as GANs. So here, for example, in our first state, we train the neural network on cats and dogs, and also we train a generative model to learn the distribution of these classes, and later generate images of cats and dogs. We can see here that the image of cats and dogs is not perfect, of course, because it's generated by an artificial intelligence, but it has the distribution of these classes that is the most important for us. So in the second state and all incremental states, they just use this generative model that they keep in a memory, and they use it to generate images for the past, and these images are mixed with the images of new data, and they update the neural network with using all the parameters of the neural network. So the advantage of this set of methods is that they have complexity that also increases slowly because we add one neuron in the classification layer each time, and they achieve the best state-of-the-art results. And this thanks to the memory. Is more specifically the methods that they have fixed size memory that they have the best state-of-the-art results right now. But the disadvantage is that Since we retrain all the neural network parameters, this takes time than just training the last layers like we do in the fixed representations. So this retraining, it means that we need to wait a little bit time until the model adapts to the new data before to be able to evaluate it. And also their accuracy depends on the available memory. So of course, the more we have memory, the more we can store images in the memory, the more the better is the accuracy. And when we don't have memory at all, it affects too much their performance. Here also you can find example of two methods from the state of the art that you can read if you are interested in this type of methods. The last type of methods are parameter isolation based methods. And here we can find fixed networks. Like I said, these networks, they don't expand the neural network, so they just share the parameters between the different classes. For example, in time step 1, when we had cats and dogs, all the network parameters are used to train the neural network to train on these two classes. Now, when we have a new set of classes, what these methods do is that they estimate the importance of the parameters in the neural networks, they sort them, and later they keep the most important parameters of the neural network. They say this is specialized in cats and dogs, and they freeze these parameters. They don't touch them anymore. And they use the other parameters that they judge non-important, and they use them to train for the new classes. So we have like shared parameters inside the same neural network, and like this, each time at each incremental state, they recompute the importance of the parameters, and they free some parameters to use them to train on more classes. There is another type of network that we call dynamic networks. This neural network, once there is a new set of classes, for example, here C3 and C4, what they do is that they create another branch in the neural network, and this branch is specialized only to train on, in this example, birds and horses. Like this, we have like parallel branches, and each branch is responsible to train on a certain set of classes, and in the end we join these subnetworks to output global prediction scores. As you can see here, the neural network is very expanding a lot as the new data appears. So the advantage of this set of methods is that also they don't depend on the past memory. They don't really need a memory to give good results. That's why also they give good compromise between past and new classes, because each set of classes, they have their own neurons, and there is no interference between the classes, and there is no catastrophic forgetting in the neural network. However, also because we need retraining and also the estimation of the importance of the parameter at each incremental state, this needs time. So also they are not fast as the fixed representations. In the case of when the neural network is fixed, for example here, as you can see, we can't learn a limited number of tasks because the neural network has a limited number of parameters. So we can free the parameters as the new classes appear, but there will be one moment that we can't anymore free the parameters because just the neural network can't divide more the number of parameters by the number of tasks. So this type of methods are really limited by the number of classes that they can learn. The disadvantage of these methods, the dynamic networks, as you can see, the architecture or the complexity of the neural network is growing exponentially, which means that with the time it will be difficult to train this neural network, and it also will take too much space in the memory, which is not practical in continual learning when we are speaking about big data. Here you can find some papers in this for this type of methods if you are interested. So to conclude, continual learning is a very interesting topic in artificial intelligence. Of course, it's not yet resolved because there is still a large gap in performance between continual learning systems and systems that are trained with all the data from scratch each time. So researchers are working on it, and it's really interesting topic to work on. In fine-tuning methods, I mean, when we fine-tune the neural network with data of new classes, the classification layer is the most affected by catastrophic forgetting. As I showed the graphics in the beginning, we can see the gap in prediction scores between past and new classes. The third one is that when we use fine-tuning based methods, it's better to use memory. Fine-tuning based methods, as a reminder, are those who update all the neural network. And fixed representation, when we fix the neural network, when we freeze it in the first state, it's better to don't use memory, because these methods, they don't really need a memory. So thank you for attending this presentation. Don't hesitate to write me if you're interested to dive deep in the details of the topic. Here in my GitHub, you can find codes for methods that we developed in my PhD for this continual learning task. Thank you, and don't hesitate if you have questions.
Bueno, gracias doctora Ida por su presentación, estuvo realmente interesante. Y pues bueno, vamos a continuar con las preguntas una por una, en lo que nos permite el tiempo. Entonces, comenzamos por la primera. What is the main difference, Ida, we're watching your screen. Okay. What is the main difference between classification, detection, and recognition tasks in artificial vision?
Okay, the classification is just when we have an image and we need to say this image, it can have many objects inside of it, it doesn't matter, but the goal is to say the main object in this image, what is it? Is it a cat? Is it a dog? For example, if we have one big cat, I will say in the image, and we have, I will say, dogs, but in the background of the image, we only care about the most important object in the image, and we say it's a cat. So it's an easy task in the sense that we don't need to say where is the cat exactly in the image, and we just need to say it's a cat. So this is the classification. The detection is more difficult in the sense that we are not only interested in one object in the image, but we are interested in all the objects in the image, and we don't need just to say what it contains, but we need to say exactly where in the image there is what is this object. So we need to draw a bounding box on this object, and we say this is a dog, this is a cat, this is whatever. And now recognition is the fact to it's used, I would say, in detection and classification, is the fact to recognize and understand what is in this image. So the facts to classify the image, it is recognition, because I know that there is a cat in the image and I recognize it and I say it is a cat. So recognition is the shared term between classification and detection, because I don't say just that there is an object, but I say it is a cat. The fact to say it is a cat, it means we recognize this object.
Okay, let's pass with the second one. What is the learning time in continual learning systems, and what is the programming language used?
The learning time, unfortunately now in the community, they don't really compare the methods based on their learning time, even if it's really important. But I would say that when I did experiments on ImageNet, it contains 1,000 classes In total, it took me around, I would say, 4 to 5 days to learn all the 1,000 classes in a continual learning manner. This, when I use fine-tuning methods that they need to retrain the neural network each time. But when I use the fixed representations, it took just, I would say, 20 minutes to learn all the data set. So we have really a large gap in the training time, from 20 minutes to 4 or 5 days, depends on the method that we use. For the programming language, most of the people use Python as programming language.
Okay, let's continue with the question by Arturo Vasquez. And the question is, the continual learning is just used for image recognition, or it can be applied in other models like NLP in order to make a general AI?
It's true that it's more popular in computer vision, but it's used nowadays also in NLP tasks. Now the continual learning community it's focused on image classification, because now the problem is really not solved yet, and there is big gap. So people start by, I would say, easier tasks such as image classification, where we find more works than object detection or segmentation, for example. There is work about continual learning, of course, in these fields, but it's less popular than classification. And there are also people that they use it in NLP, for example, to develop incremental text classification, or even incremental generation of data, if it's text or image. So yes, it is used, but it's not so popular as the continual learning for image classification.
Okay, let's continue with Jonathan Rodriguez. Why artificial intelligence fails so much?
It's because, as I said, the problem is that the catastrophic forgetting was something that was not expected as a behavior from the neural network. So it's just a topic that people are trying to understand. And the main reason behind the catastrophic forgetting is that the fact to retrain the neural network, when we do these rehearsal steps using the data of new classes, we erase completely, we update the neural network based on this data, and this update of the weights is not measured in order to keep knowledge from the past. So this is it. The fact to retrain the model and update the parameters with data that is available right now will make the neural network just shift to learn the new classes and just forget what it was not before. But I mean, thankfully now there is lots of researchers that are working on it, and there are many solutions that reduce the gap with the classical training. But the results are though still not enough to use these continual learning algorithms in real applications such as autonomous cars, because it's so dangerous, the mistake in this kind of system.
Okay, thank you. We continue. Can we add as many new classes as we want?
Theoretically, this should be the main goal of continual learning algorithms, but this depends too much on the type of the method that we are using. As I said, there are two methods that are so difficult to scale, are the fixed representations, because when we have data that have a large domain shift, with the fixed representation, it's not be possible to scale. It won't be possible to learn an unlimited number of classes. And also the methods that they are fixed neural networks and they are based on parameter isolation. As I said, they share the weights parameters of the neural network between different classes. And in the same time, they don't expand the neural network. So there will be one moment that it won't be any more possible to share these parameters because they have a limited number. But if we take methods that are based on fine tuning, for example, they are more robust to go to scale and learn too much classes as we want.
Okay, we have one question, another one. First, he said congrats, and the question itself is where or what do you recommend us to study these models deeply?
Okay, so I recommend you, there is one community of free access that is called Continual AI. I will write this in the chat. Continual AI. This community, they give courses for free for continual learning. There is a conference each week about continual learning methods. I think it's Thursday afternoon. Morning for you in Mexico, and they give lots of content. They also have Slack to speak about and discuss about continual learning, and they have also developed continual learning framework that they call it Avalanche to train many types of algorithms continually. So for me, I really recommend you to stay in touch with this community, and you will learn a lot from the courses that they give and the talks every week that they propose.
Well, the other one is not a question, but it's a request. I mean, if you can share with them your GitHub again in the chat. Sí, lo está buscando y ahorita pasamos al... Okay, la otra pregunta es, have you worked on a project with continuous learning?
Yes, in fact, my thesis, it was about continual learning, and I think we had like around 8 or 9 papers about it. So if you just connect to my GitHub, you will find one repository that is called Class Incremental Learning, and there you will find all the methods, the papers, the codes, and the data if you want to reproduce the results. And this was mainly the project of my thesis.
Okay, we have another question from Gerson, and he said, what do you think will be the future of machine learning holds? What do you think the future of machine learning holds?
Well, I think that already the machine learning is now a must in this world. That we can't live without it now, even if we don't want to. So I think that really the artificial intelligence and machine learning are taking really a big part of these technological advancements. And I think the future will be really just deep learning, machine learning, and artificial intelligence in all the senses of and all the applications of the real life.
Okay, let's go with the last, looks like the last question, and it's by Gerardo Martinez. He said, I have seen AIs that generate images with a single text input, like DALLE. Do these AIs use a neural network like the ones present here, or are these systems more or less complex? Thank you.
To be honest, I don't know this system, so I won't be able to answer this question because I simply don't know. Maybe they take inspiration from some methods, but since it's a different task, I guess they have to adapt these methods in order to be able to make them work, because really some of these methods are really designed for image classification and can't be adapted, and others yes, but the exact answer I don't have it. I'm sorry.
Maestra Carmen, ¿procedemos con la lectura del documento o hago la última pregunta?
Procedemos a la lectura por los tiempos que ya los tenemos encima. Adelante, por favor.
Ok, está bien. Doctora Aiden Belouadah, de Datakalab, el comité organizador del Cuarto Congreso Internacional y 12º Congreso Nacional de Ciencias de la Computación CONACIC 2002 le agradece su invaluable apoyo en impartir la conferencia magistral titulada Towards Machine That Can Learn Continuously el día 5 de octubre a las 11 horas en modalidad virtual. Sin otro particular, le agradecemos sus atenciones y el honor de compartirnos sus conocimientos a nuestra comunidad académica y científica. Además, su constancia será enviada vía email y, bueno, la podrá tener en pocas horas. Muchas gracias por su invitación, por invitarme también a mí. Y pues, bueno, gracias por todo, Benemérita Universidad Autónoma de Puebla y CONACIC 2022.
Thank you for inviting me. It was a pleasure to be here with you. Thank you.
Thank you very much, Doctora Iden.